we're going to start with these two here. Okay, so let's start with a mass on a frictionless horizontal surface. And let's say it's 10 kilograms. If it's just sitting there, what do we know? Well, there's a force of gravity on it, and there's a normal force pushing it up. And these two forces are equal and opposite pairs. They're Newton pairs, right? No. Of course, they're two totally different forces, but they are equal and opposite if what? The acceleration is zero, if it's just sitting there. Now, I can come and I can put a force on this box in this direction, and that force will cause it to accelerate. I'm going to label an axis. This is the x direction, and this is the y direction. I also know that if I put a force on it in this direction, for instance, if I pull with some tension, it's going to affect the normal force. The harder I pull upwards, the smaller the normal force needs to be in order to be in equilibrium. And we see that if I pull up on someone standing on a scale, the reading on the scale goes down. So what happens if I pull at some angle in this direction? The cool thing about a rope, ropes can only pull along the direction that you pull them. And so what's neat about a rope is if the rope looks like this, the force is in that direction. And so now we have a situation where I can break this tension up, tension in the x direction, and tension in the y direction. And this tension is a horizontal force. So there's a force pulling it this way, and there's also a force pulling it that way. And they both act independently. We can look at this holistically, or we can look at this component by component. So holistically, all we need to do is add all these vectors together, and we should get mass times acceleration. So the sum of the forces must equal mass times acceleration. So for example, before I pulled on the string, I had just the force of gravity pulling down and the normal force pulling up. And it was in equilibrium. But now I have another force, this tension. I'll start with this tension in this direction, plus the force of gravity, okay, plus the normal force. And the thing is, I don't know what the normal force is, but I do know, oh, this is a dynamics problem. I have to ask myself that question. What is the direction of acceleration? And I can see this box is not going to accelerate upward or downward. It's accelerating this way. So I'm going to write here the acceleration is in this direction, because that tells me that is the direction of the sum of the forces. And so I know in order for it to accelerate that way, the force, the vector sum of the forces must be in that direction. So I know the normal force must look like this. And now when I add all those vectors together, this is the vector sum of the forces, which is equal to mass times acceleration. And if I pull harder, what changes? Well, gravity is the same, but the normal force will have to be less to get me into equilibrium in the vertical direction. And the total force will increase. So the harder you pull on this, the less the scale under it would read, and the more it will accelerate on this frictionless surface. But you can do this component by component. Another way of writing the vector sum of the forces is mass times acceleration, is that the sum of the forces in the x direction equal mass times acceleration in the x direction. And the sum of the forces in the y direction equal mass times acceleration in the y direction. And so now we just look in terms of components. In the x direction, 0, 0, ah! The tension has an x component. So I would just write tension in the x direction equals mass times acceleration in the x direction. And then we look over in the y direction. And we have 1, 2, 3 forces in the y direction. So we have force normal plus the force of gravity plus tension in the y direction equals mass times acceleration in the y direction. Now there's two very important things. And this goes back to why we ask our question. Which way is the acceleration? It's in this direction, so we know this is 0. And the other part is in choosing a direction, this is the positive x direction, and that's a negative. This is the positive y direction, and this is a negative. So the accountant comes out and says, wait, in the x direction, tension is positive. In the y direction, the y component of the tension and the normal force are positive, but the force of gravity is acting in the negative direction. And now I can solve for the normal force equal to force of gravity minus the y component of the tension. So this makes sense to us because the harder I pull it, the smaller the normal force is, or the smaller the reading is under the scale. And you could imagine if I pulled it hard enough, this component could become greater than gravity, and all of a sudden I would be accelerating this off the ground. And so, for instance, if this is a realistic scenario, what if this tension is equal to 100 newtons, let's say? Well, then this would be about 70 newtons, and this would be about 70 newtons. So my acceleration in the x direction would be about 7 meters per second squared, and the normal force pushing upward would be equal to this 100 newtons downward from the force of gravity minus how much I was supporting. So it would be about 30 newtons upwards. And so you can say, what's going to happen then if instead I pulled at some angle like this with my 100 newtons? And then you can estimate it. Maybe this is about 10 newtons. And then this would be much bigger, close to the full 100 newtons. Maybe 95 newtons, more or less. And now we'd have an acceleration close to 9.5 meters per second squared, but the y component of the tension is very small. And so the normal force would be close to 90 newtons. Now you may ask yourself, why is it we chose x and y for our independent coordinates of tension? Or why didn't we just make this the x direction and break up force of gravity into its perpendicular components? Why did we choose horizontal and vertical? The key to that answer lies in this very important question. What's the direction of the acceleration? So for instance, if instead of being horizontal, the surface was on an incline, and now if you had your box here and you pulled at that same direction, let's say not hard enough to pull it off the surface, we would say, the acceleration is in this direction. Then we would make this our y component and this our x component. For the very simple reason that acceleration is in this direction, and in this direction, acceleration equals 0. So the vector sum of the forces in this direction is 0, and it's independent from the acceleration.